thank you everyone for being here on Thursday morning for you. This is the last lecture on wind turbines, and I'm going to tell you a little bit about the electronics and the control side of wind turbine operation. This is not my area of expertise. I am a mechanical engineer and aerodynamics person, so I can talk a lot longer on blade design than I can on these parts of a wind turbine. But one thing that's very important that I've learned over many years of being involved in renewable energy is that even if you're a professional working in the area of renewable energy in a specific field, you have to be aware of the fields that surround you. In other words, as someone who designs wind turbine blades, I need to know enough about generators and control systems and power electronics so I can see how they interact with each other. Because that interaction is extremely important. And in the case of wind turbines, it is very much the case that all components of a wind turbine are designed concurrently. And so there's very big interaction between large numbers of highly trained professionals that do that design and construction work. So I'll talk a little bit about the generator and the power electronics. And I'll start off with, and this will be a fairly simple exposition because, as I said, I'm a mechanical engineer. I won't be able to go through the details of the electronics and the control theory, but I can give you enough of an indication. So I've mentioned this before. I'll see if I can get my laser pointer going. There's basically two types of generators that are used on wind turbines. There's a permanent magnet generator or similar type of generator. I've mentioned before that these generators are almost entirely the generator that's used in offshore wind farms. And the reason for that is that they are direct drive generators. I showed you the inside of a direct drive generator in a previous lecture. They do not need a gearbox, and a gearbox is a high maintenance component of a wind turbine. So offshore turbines have migrated virtually exclusively to permanent magnet generators. When we come to onshore turbines, land-based turbines, it's more common at the moment for the generator to be an induction generator. And an induction generator, it tends to be cheap. There's a lot of knowledge on these sorts of generators, which are actually quite similar to an ordinary electric motor running in reverse. The most common form of induction generator for a wind turbine, a large-scale wind turbine, is a doubly fed induction generator. And part of the reason, as we will see, is that a doubly fed induction generator can be partly controlled directly from the electricity grid. And what I've shown on the bottom right-hand side here is a little diagram of torque versus the generator shaft speed as a fraction of what's called the synchronous speed. Induction generators are called asynchronous generators because the frequency of the power that they produce is not directly is not just the shaft speed. There's a factor involved. With a permanent magnet generator, the power frequency is directly equivalent to the synchronous speed. Because with an asynchronous motor or generator, it can do either. So a common electric motor can be used as a generator for a small wind turbine. All that needs to happen is that the generator shaft speed as a fraction of the synchronous speed goes from less than 1 to be for a motor to be greater than 1 for a generator. And typically both motors and generators operate fairly close to the synchronous speed. Typically there's what they call slip. The difference between the actual shaft speed and the synchronous speed is typically only a few percent. As I said, doubly fed induction generators, which I'll show you a little bit about in the following slides, are very common for land-based large wind turbines. Okay, here's the inside of a permanent magnet generator. This is a generator whose characteristics are shown on the right. So this generator will produce something like 750 watts at a speed of 550 RPM. It's about 30 centimeters in diameter, so it's quite a small turbine generator. And you can see that the main shaft of the generator comes directly out of the housing for the generator. And for a small wind turbine, probably with blades around about 1 meter long, those blades can be directly connected to the generator shaft. If I open up the generator from the back, you can see here the rear bearing of the generator, which we've taken out of the housing here. And here you can see the rotor of the generator, which is cast iron, painted to protect it from rust. And you can see the permanent magnets glued to the outside of the rotor. And then just above the permanent magnets are the windings, which produce the power. And you can see 3 cables coming out from the windings here, because even a very small permanent magnet generator will produce 3-phase power. 3-phase generators are universally used on wind turbines of all size, partly because the power per unit weight is significantly higher for a 3-phase generator than for a single-phase generator. So what you see on the right-hand side here, plotted against the generator speed, the output power, which is the blue squares, the generator torque, which is shown on the bottom line there, and the generator efficiency that you can see up here. So this generator, small generator, will have about a 74-75% efficiency. Though that's a low efficiency, we're going to see when we talk about much, much larger generators that they have efficiencies well over 90, 97, 98%. But when you get down in size, typically speaking, the smaller the generator, the less efficient it's going to be. And added to that, the efficiency drops off substantially when it's partly loaded. These are some of the issues that are very big challenges for building small wind turbines, which I've done a lot of in my time, but they don't particularly concern a large wind turbine. What I've highlighted here, 754 watts and 550 RPM, is what I've taken as a design example. I'm not going to show you the details of this because it would take too long and not be particularly useful for this course. But I've taken this as a design example for how to match generator and blades for a small wind turbine design. And most of what I'm going to be talking about is independent of whether it's a small wind turbine or it's a large one. So what I've done here from these generator characteristics, I've arbitrarily said that I'm going to take the rated conditions, that this turbine is going to produce a rated power of 754 watts at 550 RPM. And then I go through, when I wrote a book on small wind turbine design a number of years ago, and one chapter is how to match generator and blade design. What I'll point out, though, is the only curve that I haven't said anything about is this black curve here. And that black curve is given by this equation here. And I'm going to ask you, what is the significance of that curve? If I've taken my rated conditions at 750 watts and I scale that by omega over 550 cubed, what does that black line represent? Okay,
Power coefficient again.
Sorry?
Power coefficient?
Yes. that cube is very important because that is the cube that appears in the power coefficient. And if we're going to get the maximum power out of our turbine, we can design it to give maximum power at these conditions here. And then at other conditions, we can arrange for the power output to be given by that equation here. So that black line is the most power that the blades of the turbine could produce. And fortunately, in this example, they fall below what the generator is capable of, because there would be no point making a blade design that extracted more power than the generator could handle, because it won't be able to do it. It will burn out, or it will do it very inefficiently. So while we go through this section of the notes, and I'm going to come back to this point, I want you to think some more about the significance of that relationship there. And what I'm saying the significance is that line is the maximum power that the wind turbine can produce as the generator speed varies. And why that is significant, I'm going to tell you about in a few slides' time. So here's just a little bit of information, somewhat old by now, so 6 years is fairly old by wind turbine standards, but the information is generally still applicable. Here are 3 types of generators. I've talked about permanent magnet generators. I've talked about doubly fed induction generators. A squirrel cage induction generator is just a standard induction generator. And if you look at the manufacturers, the generators, the size, you will see that typically the permanent magnet generator is used on the larger wind turbines because they're the ones that are placed offshore. If we look at some of the characteristics of large generators, we can see what happens if we change the generator shaft speed. There's a direct relationship between the number of pole pairs in a generator, and that's true whether it's an induction generator or a synchronous generator. So the faster it goes, the fewer poles it requires. So sorry, I think I've actually got that round the wrong way. But anyway, they're the pole pairs for that two conditions. And what I want you to really pay attention to is the efficiency values here. So we're talking about, at the megawatt size, we're talking about generators that are around 98% efficient. So much, much more efficient than you can get at the small scale. Here's some of the reasons for the losses. There are copper losses in the armature. There are iron losses in the rotor frame and things like that. And down the bottom here, you get an idea of both the mass of the generator and its cost. So the generator cost is, roughly speaking, comparable to the cost of one blade. So it is a significant cost for a wind turbine. Okay, now we come to the crunch, the really important issue that I want you to appreciate. And if you don't understand what I'm saying here, please ask me again to explain it, or send me a notice in the chat, or send me an email. What I've shown, or what I've taken in the top diagram at the left, is a typical plot of the power coefficient versus tip speed ratio. Okay, this is the peak power occurs at a relatively high tip speed ratio, but that's not really important as far as this explanation goes. What is important is that peak optimal tip speed ratio, where you get the maximum CP, is where you want to operate as much as possible to extract the maximum possible power from the wind. In other words, for any wind speed, this point here is where you want to be to get maximum power. And the difficulty for wind turbines is that the tip speed ratio equation involves the wind speed. Sorry, I've changed symbols on you. U is the wind speed here. So that as the wind speed varies, you need to vary the generator shaft speed in order to keep the tip speed ratio constant. Okay, and the next crucial piece of information is that adjustment of the tip speed ratio has to occur without measuring the wind speed. Okay, large wind turbines do not have access to the wind speed. They measure the wind speed on top of the nacelle, but that is the speed of the wind that has come through the rotors and had some of its power extracted. So that's not representative of the free wind speed. So what we try to do in the major power producing part of the power curve is to keep the tip speed ratio constant to maximize the power, which will give us a power that varies as the generator frequency cubed. And that's where the black line in the previous lecture comes from. So what we want, of course, is that our angular velocity of the turbine will be the maximum angular velocity times U divided by the wind speed for the maximum angular speed. Okay, so the problem is, how do we achieve this without measuring the wind speed? And this is a very similar issue to what happens with photovoltaics. When we get on next week to the section on photovoltaics, we will see that this challenge of keeping the maximum power production while the conditions vary is very similar for photovoltaics as it is for wind turbines. And I'll tell you in the section on photovoltaics, I'll tell you how it's done there. So what I'm going to do is stop sharing the screen, because I'm going to share the screen again and move to my whiteboard. Okay, so you should be able to see the whiteboard. Okay, so what I've drawn on the whiteboard, and I'll be looking down to the left on it, is a power curve. So let me change the symbol to the one that we've just used. U is the wind speed. So there is a typical power curve for a wind turbine, and we're interested in this region here. Okay, because this is the region where the wind turbine spends probably 95 to 97% of its time when the wind is blowing. And that is the region where power is approximately proportional to U cubed. And now we know the reason why. Okay, so what I'm going to tell you about now is how the control system attempts to produce that power curve without actually measuring the wind speed. If you could accurately measure the wind speed, you wouldn't have to go to this extent with the control system. And a lot of research that is going on in wind energy at the moment is to look at techniques by which wind turbines can actually measure the wind speed. Okay, so what we're going to do is look at how this curve transforms if I make it a curve of power versus either frequency or shaft speed omega. Okay. The reason that we do this is, I've said, and I've emphasized it, that the wind speed can't be measured. However, if we transfer this curve to a power versus frequency, then that is not going to change the shape of the curve in that region there. Okay. It's not going to change the optimal or maximum power curve. Okay, so if this power curve here is generated by the maximum power coefficient, then we can translate that into an equivalent optimal power curve for power versus frequency or shaft speed. It doesn't particularly matter which. Why these two quantities are considered here is that they are both very easy to measure. Okay, the instantaneous output power from a wind turbine is very easy to measure. It's usually measured straight from the generator or after the rectifier. Similarly, the frequency of the output power is easy to measure. So that means that in terms of getting the maximum power point, as it's called, or points along that blue line there, we know where they are. And so what typically happens in a wind turbine control system is that the power and the frequency are sampled, and they're sampled probably every second or so. And when you sample the power, you might get a point that's there. Hopefully you don't get a point that's on the left of this curve, because that would mean that you're getting more power than the designers had intended. But say we measure the power there. And what the control system then consists of is a strategy by which we move towards the optimal curve. That is called, and this is a very important term in renewable energy, that process is called maximum power point tracking. As the wind conditions vary, we want to keep extracting the maximum possible power. Maximum power point tracking as a strategy is so important that people refer to it by its initials, MPPT. And we're going to see how maximum power point tracking is done for photovoltaics in the next few lectures. How it actually does this, I don't know how many of you are familiar with control systems. What the most common way in which this aiming to get back towards the optimal curve is done is to do some sort of what's called perturb and observe system. So perturb means to change it. So you change the operating system of the turbine. So you load up the generator a bit more or a bit less, and you see whether your operating conditions are moving towards that line. Okay, a very simple method in theory. Sometimes it's called hill climbing because the top of the hill is your maximum power point. Very simple in theory, actually quite complicated to do in practice, because what can happen in practice is that the wind conditions can change between deciding how to perturb your system and then measuring the outcome of that perturbation. So it's one of those things where the basic idea is quite straightforward, but there's a hell of a lot of very detailed work to transfer that simple idea into a usable technique. Okay, so have a final look at that slide, because I'm going to stop sharing the screen now and go back to the PowerPoints in the lecture. And let me turn the laser pointer on again. Okay, so what I just showed you on the whiteboard is how, in very general terms and very simple terms, how a wind turbine attempts to stay at that point as the wind speed varies. Now, how it does that, I'm not expert enough in the technology to tell you. I know the basics of how it does it, and I'll give you a partial explanation for how that happens as we go along. Okay, what you see here is two topologies, as they're called, of the power electronic system of a wind turbine. So here we have an induction generator. This is particularly a doubly fed induction generator, and you can tell that it's a doubly fed induction generator because it has a direct connection to the grid. I don't know enough about the theory of doubly fed induction generators to know how that works, but I do know that people tell me that there are advantages in those operations. Down the bottom, we have either another type of asynchronous generator with a gearbox, or we have a synchronous generator with like a permanent magnet generator. And what I'm pointing out by showing these two types of generators is that the power electronics part of it is very much the same. Okay, the power electronics that are involved, that are used in wind turbines, are pretty much independent of whether you have a permanent magnet generator or an induction generator. So the way it works is that there's usually a rectifier which changes from AC to DC. And the reason for that is that as the wind speed varies and we're tracking the maximum power point, the generator frequency and voltage is changing all the time. Okay. We want to, in general, be transferring that power to the electricity grid, which has fixed frequency and voltage. So there's no way we can directly couple the output of the generators to the grid. We have to do this power electronics process where we go from rectifier, where we rectify. This is often called the DC bus, with a capacitor in there to reduce the essential or the ripples that you'll get in the DC power coming out. And then there's a conversion from DC to AC. So the AC that comes out of this process here is very close to what is required for the electricity grid. Okay, and you can see that that is done both for asynchronous as well as synchronous generators. And in addition to doing that, the power electronics has to fulfill the maximum power point tracking. So it's actually quite a complicated system that we have here. And I'm going to stop the presentation on wind turbines for a little bit and just talk about power electronics in general. And the reason I'm doing this is that the power electronics are absolutely essential to wind turbine operation, and they're absolutely essential to photovoltaic operation. And there's a very good argument that you can make that it's really the development of power electronics that has enabled those renewable energy technologies to become widespread and cheap. Now, that's not entirely correct because we need cheap photovoltaic modules and we need cheap wind turbines as well. But it would not matter if we had cheap wind turbine blades and cheap photovoltaic modules if we didn't have good power electronics. So what I'm going to give you is a little bit of a history and an idea of the future of power electronics. Unfortunately, this is quite old. This is 2016, which is 5 years old now, and power electronics is changing more rapidly than wind turbine or wind energy. Unfortunately, I haven't found another source of what I think is really interesting information in this presentation. Enphase will meet again. They're an American company that makes what are called microinverters for photovoltaics. And I'll talk about microinverters for photovoltaics later. Okay, so here's a little bit of history about power electronics. And what we mean by power electronics are simply electronics that can handle relatively large amounts of power. Interestingly enough, the term power electronics didn't exist before 1973. Okay, so we're actually looking at a technology or an enabling technology for renewable energy that is relatively recent. And there's a little bit of more history there, a couple of diagrams that show what some of the power electronics looks like. Here's a typical circuit. I won't go into that because I wouldn't be able to enlighten you anymore on that. Here is looking at what is happening with the history and the performance trends in the power electronics industry. Control complexity. Okay, that is hugely important for wind turbines because maximum power point tracking is not a trivial exercise. Conversion efficiency. If we don't have high efficiency of conversion from the generator AC to the grid AC, then power electronics are not going to be very useful. If the conversion efficiency was down around 50%, there probably wouldn't be a wind industry. Okay, most power electronics now, and I'll give you an example at the end of this lecture, typically greater than 97% efficiency. The power density is much higher now. And of course, that is very important as well, because that correlates with the size of the controller as well as its mass. And as if you remember back to the very first lecture, I showed you that, or maybe the first lecture on wind energy, where I showed you that some of the power electronics for a wind turbine is up on the nacelle. So mass is important. Switching frequency. Now, you guys probably know what I'm talking about here. Often the people that take my course in Calgary on renewable energy are mechanical engineers like me. So I would have to explain a bit more about what switching frequency is. It's basically the frequency at which the power electronics can change from one state to another. And the significance of that, I'll show you in the remaining lectures today. And of course, cost is hugely important. Okay, the wind industry and the photovoltaics industry are incredibly cost competitive. And so anything that can reduce the cost of the final product is important. Okay, so here is some predictions about what's going to happen with power electronics. And you can see, I think, get some idea that, yes, they are becoming more important. Microwave ovens now for kitchens often have power electronics in them and have an inverter-based power electronic system. Air conditioning systems often have a power electronics inverter system as well. So they're becoming much more common, and I think that trend will continue. On the horizon, there are a lot of new technologies that are available. One of the issues with power electronics is the losses that are associated with the switching of them. And a lot of the research and development that's going on at the moment is aimed at reducing those losses. Okay, so I'm going to probably review some of the information that you would have learnt about how to convert from three-phase to single-phase power. Because by doing this, I set the scene to at least give you some understanding of how maximum power point tracking can be done. So this diagram shows what's called a simple three-phase diode bridge rectifier. On the right here, we have V1, V2 and V3. They're the three phases of the generator, and associated with each of those will be a current. And this bridge rectifier simply has 6 diodes in it. And a diode is an electronic device that allows the current to flow in one direction only, in the direction of the arrow head here, and that line there tells you it can't come the other way. So this is just about the simplest way in which you can convert a alternating current into something approximating a direct current. The problem with power electronics is that any device like a diode or a switch will have a voltage drop across it. So there is an efficiency price that you pay for the power electronics. As you can see from the numbers that I'm quoting, around 97%, a hell of a lot of work has gone into minimizing those losses, but they are still there. Okay, so what you see here on the left is the 3 input phases to that circuit, and on the right, VA is this voltage up here, VB is this voltage here, and this is what VA and VB look like. So we've sort of converted AC to DC, but of course, we haven't done it perfectly because that's actually physically impossible. You can see a voltage ripple, as it's called, like a ripple on a pond when the wind blows over a pond or you throw a stone into the water. That voltage ripple needs to be removed as far as possible, which is one of the reasons that after rectification, most power electronic systems have a DC filter on them to remove that ripple even more. Okay, what's you see here, as I said, is the absolute simplest thing that you could do to an AC output voltage form in order to transfer that to a DC voltage. Now, there's a problem with this. I've mentioned, well, there are problems, more than one problem. One problem is the voltage ripple that I've mentioned before. The other problem is that with this conversion, you have no control. Okay, whatever AC voltage comes in at whatever frequency, it will be converted to a corresponding form like that. You're not actually able to control the generator producing these waveforms in any way that gives you something like maximum power point tracking. So this is where modern power electronics comes in. And here is a very simple explanation of how that might be done. This is not a complete explanation. It's just meant to give you an idea of what the complicated power electronics and control algorithms do. So imagine on the left-hand side here, we have the nominally DC voltage coming out of the rectifier. Here we have an inductor. Here we have a diode. Here we have a capacitor, and that will give us an output voltage. And we're going to concentrate on this device here called a switch. And all that switch does is open and close. And it opens and closes at a particular frequency, which is called the switching frequency. And this is the schematic of one of the most common forms of power electronic devices. It's got IGBT, stands for a number of things. It can be isolated gate bipolar transistor is one of the interpretations of that symbol. It's a relatively old power electronic device, but one that is at the moment the most common one used in wind turbine power electronics. So if the input voltage VDC is the output of the rectifier, then the output voltage is scaled. The output voltage is that voltage scaled by this factor here, 1 minus A. And A is called the duty cycle of the switch, right? And the duty cycle is simply the fraction of the time that that switch is shut. Okay, so by controlling the duty cycle, we begin to be able to control back to the generator. And the important thing, and this is something that will come up in the next couple of slides, so please remember this, switching frequencies are high. They can be up to 20 kilohertz, which is pretty much on the edge of hearing. If you ever get a chance to visit a wind farm, you can actually hear the power electronics converters switching at that high frequency. And by varying either the frequency or the duty cycle, we're able to exert some sort of control on the power that's coming in to that IGBT. this is what the setup looks a bit more like in reality. So here is the generator. So this is what's called a back-to-back converter. And the first back, this part here, is the rectifier part. So the first 6 IGBTs here, which are nearly always combined with a diode, have the job of rectifying the 3-phase input power to DC. It goes through the filter here to remove as much as possible the ripples. And here is the other side of it, the grid side, where the inversion occurs. So this is pretty simple structure, but it is generally a very common one that's used. Okay, the way it works is as follows. All these devices here do switching. Okay, they are either on or off, and the time that they are on or the frequency of the switching can be varied. And the way it works is using a technique that in English is called pulse width modulation. Okay, and the way it works is as follows. Imagine we have a back-to-back converter that looks like this. Coming in to this side of the converter is an approximately constant voltage, whose magnitude would be given by the limitation of the voltage, the maximum voltage here. And what happens in the inverter side is shown by the blue pulses that are shown here. And the red line that you see here is the desirable AC output voltage. And what is really brilliant about the idea of pulse width modulation is simply that the width of those pulses is proportional to the AC voltage that you want coming out of the device. So when we get to the part of the cycle with the maximum AC voltage, the pulses have their maximum width. When we get down to 0 AC voltage, they have their minimum width. And remember, the frequency with which these are switching is much, much higher than the 50 or 60 hertz grid frequency. So the actual width of these pulses, you wouldn't actually be able to see if they were drawn at proper frequency. And so what that means is that the blue effectively switched DC voltage has the same voltage characteristics as the AC voltage that we want to get out of the system. And so all that happens after the converter is an output filter. And you can imagine that if these pulses are typically switching at 20 kilohertz, and what you want out of the converter is, say, 50 hertz, then it's a very easy process to filter the pulses to get the red output curve. So it's a really beautiful technique that relies largely on the development of modern power electronics with high efficiency and very high switching rates. Both of those things are essential. And that's basically what happens. And so if you look in a little bit more detail at what happens in a wind turbine control system, so again, this is pointing out that it doesn't matter which type of generator you use. The power electronic side of it and the control side of it looks very much the same. And you can see both the connections for the level 1 control all involve pulse width modulation. And you can see that in addition to pulse width modulation for the grid side of the converter, they also do it for the rectifier side. And that, in combination, is what gives the maximum power point tracking capability to the turbine. Then we have a further level of control. So at this point here, this is where the control that's associated with the pitch adjustment of the blades for power limitation at the top of the power curve. And it's also where some of the decisions are made about what to do with the turbine if something happens to the grid. Okay, the absolute worst thing that can happen to a wind turbine from the electronic side is that the connection to the grid is lost. So, but because then basically the wind turbine is producing power and that power has nowhere to go, right? So a turbine has to be able to island, it's called, make itself an island separate to the grid. On the other hand, if there are minor changes to the grid, we don't want the turbine to trip out because wind turbines are proved to be very valuable in what is called grid support. So if there's a relatively small drop in the grid voltage, you want the turbine to be able to ride through that fault and help support the grid. So this level of control has to give some value to the electricity grid if it is having trouble. But if there's a catastrophe with the grid, if you lose the grid, it has to protect the turbine. So that's the second level of control there. And then the third level of control often is a response to the system operator. So this TSO stands for the technical system operator. And that can be things like if you have an electricity grid with a large amount of wind turbines on it and it's a very windy day, the wind turbines may be producing too much power for the grid to handle. And so the system operator would issue a command to the wind farm to say, curtail, cut down your power so that we're not producing excessive amount of power. Then there's a whole bunch of issues that I find fascinating because I don't really understand them. There's the issue of what's called inert power inertia. And this comes about from the fact that with the advent of renewable energy, the nature of electricity grids is changing. Okay, electricity grids of old had a few centralized large power station and then big distribution networks to all the consumers. Wind farms and solar farms don't produce as much power as a large coal-fired or gas-fired power station. So the generation on modern electricity grids is much more distributed. And in addition, the big generators that are used on coal-fired power stations have a lot of inertia. Okay, they're huge machines. And if there is a problem with the grid and the grid frequency starts to drop, the mechanical inertia of the generator actually helps to support the grid. Now we're moving to a scenario where we're getting rid of the large centralized power stations and putting in a lot more wind farms and solar farms. And this type of power electronics effectively decouples the inertia of the turbine blades from the grid. So we have to actually introduce effectively a false inertia to the grid. And that's, again, able to be done by very fancy power electronics and fast communication. Power quality is another issue as well, which often involves the generation of reactive power, particularly if a wind farm is towards the end of an electricity grid. That's not something I know very much about, so I won't say anything more about that, and I hope there won't be any questions on that because I probably won't be able to answer them. Okay, so the final slide for tonight just shows you typical efficiency of an inverter. This is a small inverter designed for, I think, about a 10 kilowatt system. And you can see that even at the small size, as distinct to the small generator that I talked about at the beginning of the lecture, the efficiency of this inverter is very high. This is when it's handling close to the maximum power for that device. Sorry, here's the power level down here. So from around 1,000 watts to 4 kilowatts, the efficiency is very high. The problem with inverters often is that when you go down to low loads, just like the generator we saw, the efficiency tends to drop off very rapidly. And the reason for that is very simple to understand. Most of the losses in an inverter come from the voltage drop across the IGBTs and across the diodes. They're fixed voltage drops. They don't depend on the power level. So clearly the inverter would be designed to have a very high efficiency when it's handling the maximum power. But as you go down in power level, those voltage drops become proportionally greater and the efficiency of the device goes down. That's often not a big problem for wind turbines because you can see that the inverter is efficient over a wide range of output voltages, but it can be a problem down the bottom end of the power curve. And it is also a particular problem for small wind turbines. So I think that is the end. Let me just see if there is. Just one more. Here are a couple of issues that have to be addressed with grid connection. Voltage flicker is a little bit like shadow flicker that we saw in yesterday's lecture, except it occurs to the voltage. Total harmonic distortion. What that means is that most electricity grids around the world require the power that is fed into the grid to be extremely close to a pure sine wave. Okay, and departures from a pure sine wave are measured by the total harmonic distortion. And most standards for grid connection will limit the amount of total harmonic distortion that's allowed on the grid. And that has a big impact, particularly on how you design the output filter from the converter and also the transformer that usually is involved in grid connection. Power factor issues can be important, largely to help support the grid at edges of the grid. I talked very briefly about islanding. Okay, what happens if suddenly the grid is lost? Okay, a generator, a wind turbine generator could be producing its full power when something happens to the electricity distribution network. There might be a terrorist attack on the power lines. There might be a huge storm that wipes out one of the pylons for the power lines and they go down. So how you control the turbine for that, how you deal with the islanding of the turbine is very important. And I also mentioned ride-through. These are the lesser faults or the lesser changes in the grid behavior that you don't want to isolate the turbine from or the wind farm from, because in many cases, having a wind farm there can actually help the grid maintain its integrity and return to its normal operating conditions. So I think that is the next slide. Yes, that is the end of the slides. So if I can find where to stop sharing the screen after all that, I will do so. There we go. Where did it go? I've lost it. There's probably a Windows command to do this, but I can't see it. Apologies for that. Let me try this way. Do that. Yeah. I didn't realize that. I can actually stop sharing the screen by closing the PowerPoint. That's useful information after about 1.5 years of using Zoom. Okay, so that finishes the wind turbine lectures for this course. So it's about 9:25 for you people. I'll finish there. I won't start the photovoltaics module or lectures till next week. But we've got a little bit of time for questions if anybody has a question they would like to ask.
I have a question again about anemometer on the hub.
Right.
So you said that there is no necessary to measure wind velocity because we know where we locate it on the power line. I mean, we could use this point tracker and it works, right?
Yes. I think I'm guessing a little bit in answering this, but I imagine the situation is that, generally speaking, the maximum power point tracking controls that the wind turbine manufacturers do a good job. And so I suspect they're happier to stay with those techniques rather than try and do something like take the wind speed that's measured on the nacelle and work out an algorithm that will translate that into the actual wind speed. Okay, because that's quite a big research topic in wind energy. How you take wind speed that's measured on top of the nacelle and convert that to the unaffected wind speed. It seems to be able to be done fairly well, but one of the problems with it is a timing issue. Ideally, you don't want to know what the wind speed is now. You want to know what the wind speed is going to be in a few seconds' time. Okay, and it can't deal with that issue directly. One of the important areas of research in wind energy is the use of LiDAR techniques, which is basically a laser scanning technique that relies on the particles of dust and whatever in the atmosphere to reflect back, and wind speeds can be determined from that. LiDARs are used extensively now for wind speed monitoring and resource assessment, partly because they can take measurements at much higher heights than an anemometer mast. But at the moment, they're far too expensive to put on a wind turbine. But you can imagine possibly sometime in the future, some method of being able to measure the wind ahead of the turbine. If you could do that, then that really changes what you can do with the control system. And I think probably, I'm guessing a little bit, I think probably one of the real values of that is not so much in region 2 of the power curve where you're trying to extract the most energy, but when you get to the top of the power curve and you have to start pitching the blades to control the power output, that can cause very large loads on the blades. Okay, unsteady forces and moments in aerodynamics are often much larger than the corresponding steady forces. And so if you know what's coming to your wind turbine, then possibly you can change your pitch, the way in which you do the pitching of the blades, to minimize the unsteady loads on the blades. And that's a really exciting prospect, because it combines unsteady aerodynamics with the control system, which is not really done well at the moment. So there, a long answer to a short question.
Thanks. So,
okay, do we have any other questions? Okay, well, on next Wednesday for you, we shall start 2 or 3, probably 3 lectures on photovoltaics, and then I'll move on to energy storage.